Now that we have an introduction to acids and bases, we will learn the steps involved in writing the aqueous net acid-base reaction. First, you need to write down the main species that are present in solution. For soluble ionic salts, that means writing the cation and the anion. For example, if we have potassium sulfate, this would be written as potassium ions and sulfate anions present in solution. So this is subject to those solubility rules. For strong acids, we would write hydronium ion and the conjugate base. Remember, we discussed that the 6 strong acids do not actually exist as their structure, but will completely form the products of hydronium and the conjugate base. We can identify these on the acid-base table by looking at the acids that are listed above hydronium. There are 6 of them. Whenever these strong acids are placed into water, they will completely form hydronium and the conjugate base. So for perchloric acid, it will produce hydronium and the perchlorate anion in water. For weak acids, we will just write the weak acid as is. So for example, acetic acid would just be written as acetic acid. Remember, using the acid-base table, we can identify the weak acids as those being listed below hydronium and above water, including water. Water can act as a weak acid. For strong bases, we will write hydroxide ion and the conjugate acid. For example, if we have the NH2- ion, this would be written as the hydroxide ion and the conjugate acid of ammonia. If we want to identify where the strong bases are, we can use the acid-base table, and we will see that these are listed at the very bottom right side of the acid-base table. For weak bases, or really weak bases, we will write the weak base and any counter ion. So for example, if we have sodium sulfate, we know that sulfate can act as a base, but we will write this as the individual ions, sodium ion and sulfate ion. Next, we have to decide with the species present if they can act as acids or bases, and we can simplify this by eliminating spectator ions. Either they will not be present on the acid-base chart, or it will be the conjugate base of a strong acid. Next, we will write the strongest acid and the strongest base on the reactant side of the equation. We will then write the conjugate base and the conjugate acid on the product side. And from these, we will decide from the Ka of the reacting acid divided by the Ka of the produced acid, or the conjugate acid, to see if the reaction is extensive with a value of K of reaction greater than 10 to the third, or an equilibrium, meaning K of reaction is less than 10 to the third. Remember, if this has a value of K greater than 1,000, then we would just use the forward arrow. If the value of K of reaction is less than 1,000, we will use the equilibrium arrow. Let's go through some examples. Say we have hydrosulfuric acid and sodium hydroxide. The first step would be identifying the species that are present in solution. We notice that hydrosulfuric acid is a weak acid. Therefore, we would just write its formula as is. Sodium hydroxide, when placed into water, is soluble, so that will form soluble ions. Therefore, we have the sodium ion present and the hydroxide ion present. Therefore, in solution, we have the hydrosulfuric acid, sodium ion, and hydroxide ion in solution. From this, we can see if we can eliminate any spectator ions. We notice that the sodium ion is not an acid or a base, so this can be eliminated from the reaction because it is a spectator ion. Therefore, with the remaining species, we can determine which will act as the acid and which will act as the base. Hydrosulfuric acid has protons that it can lose, so it will participate as the acid. We also know that because it is listed in the acid-base table with an acid dissociation constant. Hydroxide ion has a Ka value that is much less than 10 to the negative 14th. Therefore, it is a weaker acid and will participate in this reaction as a base. In step 3, we will write these components on the reactant side, and we will determine the conjugate acid and the conjugate base. The acid will donate a proton to the base. Therefore, the acid will produce the conjugate base of hydrogen sulfide ion. Hydroxide base will accept that proton, so the conjugate acid formed is water. Lastly, we need to determine whether the arrow is going to be forward or in equilibrium. And to do that, we have to calculate K of reaction. In order to do this, we find the Ka of the starting acid, the acid on the reactant side, and divide by the value of the Ka of the conjugate acid, or the acid on the product side. We can use the acid-base table to find these values. When we do that, we calculate 1.0 times 10 to the negative 7th divided by 1.0 times 10 to the negative 14th, and we get a value of 1.0 times 10 to the 7th. This value is greater than 10 to the 3rd. Therefore, this reaction will exist in the forward direction. It will not exist in equilibrium. We will represent that with a forward arrow. We can go through another example here. We have ammonium chloride and sodium sulphite. First, we need to decide what the species are that are present in solution. With ammonium chloride, this is a soluble ionic salt. So we would have ammonium ion and chloride ion present. With sodium sulphite, this is also a soluble ionic salt. Therefore, we will have sodium ion and the sulphite ion. Therefore, looking together, we have the ammonium ion, the chloride ion, the sodium ion, and the sulphite ion in solution. Next, we can see if we can eliminate spectator ions. We know that sodium ion is a spectator ion already, but chloride ion will also be a spectator ion, and we will explain why this is in a subsequent slide. Therefore, with the remaining species, we have ammonium ion and the sulphite ion. The ammonium ion has acidic protons that it can donate, so it will be the acid. Sulphite ion, therefore, will participate as the base in this reaction. In step 3, we will look at writing the acid and the base and determining the conjugate acid and the conjugate base. The acid will donate a proton to the base, therefore the conjugate base of ammonium will be ammonia. And the sulphite base will accept that proton, so the conjugate acid that is formed is the hydrogen sulphite ion. Lastly, we need to determine whether this is in the forward direction or if it exists in equilibrium. So we will have to calculate the value of K for this using the values of the acid dissociation constants. Therefore, the Ka of the starting acid, ammonium, is 5.6 times 10 to the negative 10th, and the acid dissociation constant of the conjugate acid, or the acid on the product side, is 1.0 times 10 to the negative 7th. Dividing these numbers, we get a value of 5.6 times 10 to the negative third. This value is less than 10 to the positive third. Therefore, this reaction will exist in equilibrium. So we will show an equilibrium arrow. Let's get back to that question. Why is chloride ion a spectator ion? It's negatively charged. It has an extra lone pair than it typically would have. So why would this be a spectator ion? Well, we can observe this by looking at an example reaction. We have the chloride aqueous ion. In water, the chloride ion would have to act as the base, and the water would have to act as the acid because it has protons that it can give up. The conjugate acid that would be formed would be hydrochloric acid, and the conjugate base that would be formed would be hydroxide. We know that hydrochloric acid is one of the 6 listed strong acids, and hydroxide we also recognize is a very strong base. We can calculate the value of K of reaction to see what this means in the context of the question. The Ka value of water, the starting acid, is 1 times 10 to the negative 14th. And the Ka of hydrochloric acid is much, much, much larger than 1. When we calculate this value of this reaction, we actually get a number of 1 times 10 to the negative 23rd. This is a very, 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 very small value of K of reaction. And therefore, instead of producing products of hydrochloric acid and hydroxide, we actually don't produce much product at all. We would actually think of this reaction as existing with only the reactants present, or the reverse direction would be preferred. Therefore, in solution, you would have chloride base present in water. So this is why chloride will act as a spectator ion. And with this conclusion, we can understand that the conjugate bases of the strong acids are so weak as bases that they will actually be spectator ions in solution. Now, looking at the acid-base table, we had shown the trends that we can see. At the very top left, we see our 6 strong acids, and on the right side, across from those strong acids, we see their conjugate bases. So those conjugate bases are so weak that they will actually be present as spectator ions, and they will not participate as bases in these reactions. The exception is for the hydrogen sulfate ion because this does have a proton that it can give up. So the exception is that hydrogen sulfate ion can actually participate in an acid-base reaction, but it won't be as a base, it would be as a weak acid. Let's go through another example. We have hydrochloric acid and potassium carbonate. Step 1, we will determine the species present in solution. We have hydrochloric acid, which once placed into water will extensively produce hydronium and the chloride ion. Potassium carbonate is a soluble ionic salt, so we will have potassium ions and carbonate ions present in solution. Therefore, we will have the species of hydronium, chloride, potassium ion, and carbonate ion present in solution. In the next step, we will eliminate spectator ions. Now that we've had this discussion, we know that the conjugate base of a strong acid will be a spectator ion, so both potassium ion and chloride ion will be spectator ions. With the remaining species, we have hydronium and the carbonate ion. We know that hydronium then will participate as the acid as it has protons that it can give up, and carbonate then will act as the base in this reaction. In step 3, we will write the acid and the base on the reactant side and determine what the conjugate acid and the conjugate base will be. When hydronium is acting as an acid, it will donate a proton to the carbonate base. Therefore, the conjugate base of hydronium acid will be water. And the carbonate base will accept that proton. Therefore, the conjugate acid would be the hydrogen carbonate ion. Lastly, to determine whether this reaction exists in the forward direction or if it exists in equilibrium, we will calculate the value of K for this reaction. To do that, we take the acid dissociation constant of the starting acid, hydronium, which is 1, and divide it by the acid dissociation constant of the conjugate acid, or the acid on the product side, hydrogen carbonate, which is 4.7 times 10 to the negative 11. When we do this calculation, we get a value of 2.1 times 10 to the 10 for the value of K for this reaction, which is greater than 10 to the third, so this reaction exists in the forward direction.